Welcome, everybody, to the USC Viterbi School of Engineering Faculty Roundtable Series. This particular Faculty Roundtable Series is with our Department of Aerospace and Mechanical Engineering, and we have three fantastic faculty members here representing that department. I'm sorry, I forgot about the Vice Chair. I'll let you introduce. I really thought you were telling me to stop. Four. My name is Paul Ledesma. I'm the Executive Director of Undergraduate Admission, but you won't be hearing a lot from me. We're going to hear directly from our faculty. I'm going to let them introduce themselves right now. And then when they are done with that, I'm going to tell you how today's events are going to go. So we'll get started just in the order in my screen. I see we're going to start with Professor Gilpin, and we'll move away all the way to the end with Ronney. So, Matt.
Hi, so my name is Matthew Gilpin. I teach our junior and senior laboratory classes. I'm also the advisor for our human-powered vehicle team, as well as our team Aspen, which is focused on getting students hands-on experience with advanced spacecraft propulsion, primarily plasmas. And I'll have to say that we actually just had a very successful presentation at the GEC conference last week, where our students actually built a plasma thruster, took thrust measurements, and presented their work to the larger EP community.
Thank you. Professor Spedding.
Hello there, my name is Geoff Spedding, and I'm a professor in Aerospace and Mechanical Engineering. This semester, I'm teaching the class Introduction to Aerospace Engineering for freshmen. And so you come here, you get your foot in the door, and you get me. And the idea here is to introduce everybody to what is aerospace engineering, and we can address some of the obvious questions about that here today. I do research in fluid mechanics, which includes flows in air and water, and the flow around submarines and the flow around drones, topics that we investigate on campus. And so happy to talk about any of that. Anyway, welcome.
All right. And last but not least, Professor Ronney.
Yeah, hi, I'm Paul Ronney. I'm the chair of the Aerospace Mechanical Engineering Department. And this is my executive vice chair, Cavalier, back there. And he participates in most of these meetings. And so I teach the corresponding course for mechanical engineers, AME 101 Introduction to Mechanical Engineering. And I also teach a senior level class in automotive engines and gas turbines and graduate courses in combustion. A lot of kids go through the stage who like to make things burn or explode. Well, I never really grew out of that stage, and now I get to make a living doing teaching and research on that subject.
And I think we should add a little bit of context. There aren't horses in your classrooms. Do you want to, this is just more of a tradition, I think, that Professor Ronney likes to have this from his particular area where he does his horses and stables, right?
Well, actually, last Sunday that we had a review session for an exam. And normally I would have it during my office hours, but I couldn't do it during my office hours during the week. So I told the students, well, okay, I'm gonna have to do it on Sunday via Zoom. And so someone said, well, could we come to the barn? So about 15 or 20 of them came to the barn. I did also Zoom it for those who couldn't make it. But yeah, so we had a little continental breakfast, and they got to meet Cavalier.
Well, that's good. So if you want horses, then it will be part of your experience.
Hey, he runs on renewable biofuel.
All right. This is how we're going to run today's session. Thank you all for joining. Well, we're going to have a talk. We're going to run for the hour here up until 4 p.m. Pacific time. I'm going to be moderating the discussion. I have a number of different questions that will take us through a little bit, maybe a little bit over half of our time, that we're going to talk about the department, the classes, the curriculum, and what you can come to expect for your time here as an aerospace mechanical engineer at USC. And then towards the end of the session, I'm going to open up the Q&A feature. So only at that point, I'm going to allow you to jump in and start asking questions. So for the time being, sit back, relax, don't touch anything. Just listen and relax. It might actually adjust or at least affirm the types of questions you want to ask or inform the types of questions you want to ask. When I open up the Q&A feature, then I'm going to have you actually insert questions in the Q&A, and then you all will upvote the questions. It'll be a democratic process. Whatever the most popular questions are, those are the ones we're going to answer in our remaining time. So thank you again for being here, and I hope you have a good time understanding this. Let's get started with, I think, what is probably the most simple question, but probably has the most complex and longest answer is, what the heck is aerospace engineering? What the heck is mechanical engineering? I'm in high school. I've never taken either of these things. They both sound kind of cool. Why are they in the same department? Give us a little rundown. What is this discipline, or the combination of these two disciplines? And I know that's a very simplified question of that, but Professor Ronney, would you like to give it a start?
Okay. The way I like to describe mechanical engineering is if you have a system that needs engineering, but it doesn't involve electrons, in which case an electrical engineer will take care of it, doesn't involve life forms, in which case a biomedical engineer will do it, doesn't involve structure of atoms and molecules, in which case a materials or chemical engineer deal with it, then probably a mechanical engineer will deal with it. Oh, and by the way, if it doesn't involve any of those things, a mechanical engineer will be involved anyway, because I know every faculty member in every department says my field of engineering is the broadest, but in the case of mechanical engineering, that's actually true. And why is that true? It's because what our core expertise involve the things that are in all engineered systems: structures, fluid flow, heat transfer, energy conversion, control systems. That's sort of all within our wheelhouse. And I like to think of, we provide a lot of the supporting technologies for a lot of these other disciplines. Let's say, for example, aerospace engineering. Geoff may disagree with me, but that's the way I like to think of it, is we are the ones that encompass all of these core expertises that every engineered system needs.
Of course, I agree heartily. Many people also ask, here's a question that Paul L. didn't ask, but I would like to answer, which is, what is the difference between mechanical engineering, aerospace engineering, and astronautical engineering, which, funnily enough, is a different department here. And in general, let's start with things I know a little bit about. Aerospace engineering, as we teach it in our department, deals with things with wings, basically. So things that fly through the atmosphere. If it doesn't fly, then it's mechanical engineering. If it does, it's either aerospace or astro, and aerospace or astro has to do with things that pass beyond the 100-kilometer line, the von Karman line, and actually go out into space. That's my rough breakdown, but I'd like to circle back to the general point also that that Paul made, which is that mechanical engineering is really the basic hardcore engineering discipline from which you can branch out to almost anywhere. And there's a subsequent question that hasn't been asked yet. What do mechanical engineers do? Everything is the answer.
Matt, do you want to add anything onto that, or do we cover everything?
That pretty much covers it. What I would say, though, as a aerospace person myself, and if you're motivated to look for a major, one of the things that's interesting about aerospace, I've always thought of it as a major of superlatives. And so these are very challenging problems. And so you're looking at things that are the hottest, highest, fastest, hardest. And so you're guaranteed to run into these really challenging, really interesting problems, not just due to the fact that, aerospace engineering, these things fly, but also the existing problems within the discipline. I think one of the interesting things that I've encountered is a lot of these easy problems have already been solved. And so you're guaranteed to be working on things that are, quite interesting and quite challenging. In all of these, mechanical or aerospace, but aerospace in particular is, my field, because of that idea that you're guaranteed to be working on something that's, sort of at the extremes.
And if I could just add one more thing, is that my undergraduate degree is in mechanical, but my graduate degrees are in aerospace, and my research over the years has been pretty much split. So I'm torn. I love both.
Well, that's a great point, and this is something I was just about to ask as a supplementary question to the last answers that you gave, which is, you've all started identifying yourself as I'm an aerospace person, and Paul, you just talked about how, like, I did both. I'm torn between these, and I think our high school students are thinking that they're supposed to have an answer to this question, and they may be thinking about other areas, like Geoff mentioned with astronautical engineering, which I can get into in a second about how you can go to another event for that. But they may be thinking about chemical or electrical or all these other things. And it was kind of tied in as far as, like, what's the right one? And do they need to identify right now? Do they have to have this figured out? I mean, I'm just kind of throwing out these thoughts to you all as students tend to be stressed out about this, because they see, like, oh, you found your path, Matt. You said I'm an aerospace person. Has that always been the answer? Like, how do I not know that?
I would say you absolutely do not have to know, and it is not expected. And so from my own experience, I grew up in the shadow of Boeing. And so I thought, oh, I'll go get an aerospace degree and work on airplanes. And I didn't work on airplanes for one day. I came to USC, I got involved in spacecraft research, and I'm actually, someone in the aerospace department, but I really deal with astronautics topics, because I actually deal with spacecraft propulsion, small scale propulsion. and in fact, test and measurement and characterization of these technologies. And so in my own experience, no, I actually found that interest and that desire and that passion to do that kind of work at USC as part of the experience. I should also say that I actually went to USC for my undergraduate degree. So I have a good experience of what it means to go to USC, especially if you're a little, confused about what you actually want to work on.
And I will say, go ahead, Geoff.
I think there's a general philosophical point here also, which it's completely impossible for any of us to know right now what we're going to be doing in 10 years' time. And even more so as you're coming out of high school. So the first thing I would not worry about is the fact that I'm uncertain. I think uncertainty is a natural state in this time, and it represents opportunity. It represents breadth of choices and so on. So this is good. The second thing is, corollary of that is that any choice that you make right now is not the ultimate final choice of where your career is going to go. You want to start off heading in some direction where you think you'll be interested, think you'll be enthused, just like Matt was joyfully demonstrating just now. And then we'll see where we go from there. And I think that's the most important criterion to use right now. What do you enjoy thinking about? Do that.
Yeah, and I was as a corollary of the corollary that I would say, keep in mind, you would typically take one of the 101 level courses, either mechanical engineering or the one for aerospace engineers, the one for astronautics or chemical engineering, whatever. But you can take any of those and that will count, towards your degree if you decide to change fields. It's maybe a little better if you pick the one that's most directly focused on your field, but it's by no means required or expected. And then the rest of really your first year will be, your math, chemistry, physics, general education. It won't really matter what other courses, it won't affect the choices for, your second and subsequent years. The other thing I just didn't realize it until just this moment, but I thought about it. Well, I have a lot of, background in mechanical engineering, and I've done research on like automotive engines, things that definitely do not fly. And then I've also done, space-related research. I've had experiments flown on 3 space shuttle missions, and I work on propulsion in collaboration with Matt. But I'm sort of in the valley, in terms of aeronautics, I'm kind of in the valley of death there. I haven't really done anything in the aeronautical field. So between the 3 of us faculty, we make one complete entire AME astro person.
Yeah, great. maybe we'll have to start putting some engines on some of our research projects, hey?
Yeah.
Paul, your answer leads me to my next question, which is, and this is naturally, I think, where we're going, which is, so how can we explain what the undergraduate curriculum looks like? How do students get started? When do they get started? And how do we help them along that evolutionary process that you just described?
Mm-hmm. Yeah, well, okay, so I'll start out. That, like I say, in your first semester, you will generally take, I say, AME 101 or 105 or the astronautics version. As department chair, I've wanted to, it was happening this way before. In fact, Geoff was a previous department chair, and we want our senior faculty to be teaching these introductory classes. And I think I can speak for Geoff as well as myself in that I choose to. It's not just because I think it's important that we do, I choose to. I really like teaching the freshmen, because your knowledge of engineering is very limited at this point for most of you. Some of you actually do have some, but for the most of you, it's very limited, and that's fine. And by the end of your first semester, you have a tremendous increase in your level of knowledge, and hopefully we've set you on the right path for the next 3.5 years. So, and then you'll take math classes, you'll take physics classes, chemistry or material science, general education classes. And then it's really generally in your sophomore year that you really start focusing on the courses that relate to your major. But within aerospace and mechanical engineering, there's only a couple of classes that I think there's one in your sophomore year, and then really not until your junior and senior years, that you have classes that relate to specifically aerospace or mechanical engineering. So you really have some time to decide. So don't sweat it. Pick, as Geoff said, pick what you think you're interested in and just see where it goes.
Any other thoughts as we guide that's a great way of the introduction to the curriculum, but can we talk about some other classes maybe that you both teach or that you know of in the curriculum that will kind of continue those students' education as they go through up division? Maybe projects that they work on as well?
I think one
Matt.
of the distinguishing characteristics of our curriculum is the fact that we have these practical hands-on projects every year. And that's true in the introductory classes, it's true in second year classes, it's famously true in the third year for juniors, and it's almost as famously true in the last year for seniors who embark on an individual research project where you actually find out new stuff, make new gadgets, and in national competitions and so on, our students have done extremely well in these. And so I think that's one of the threads that runs through the curriculum that students appreciate and that employers appreciate at the end of it all. The fact that the students can be guaranteed to have had a certain level of practical education and experience, deliberate education of skills that allow them to come out the end as sort of semi-functional engineers.
Yeah, and I just like to add, I want you to speak to that, Matt, because you teach that class. But just before that, so it is definitely something that we advertise as being part of our product distinction, is all these hands-on experiences that you get, in our program. However, be careful of what you wish for. You may think this is great, and it is great. In the long run, it's great, but it's like sometimes it'll feel like spinach. Now, I happen to like spinach, but just the metaphor is that kids don't like spinach, but your parents told you to eat it. It's good for you and all that. But at the time, you may think, my goodness, mech ops or senior design project, this is a heck of a lot of work for the same number of credits as easier classes. But I guarantee you, employers will appreciate that. And as Geoff said, we do very well in these national student paper competitions because of what our students have learned in these classes. And with that, I think Matt should talk more about those hands-on classes.
Sure. And to Paul's point earlier about how that curriculum develops, a lot of those early classes, you're learning how to speak the language. So you're learning these fundamental building blocks that apply to astro, aero, et cetera. When you see me, when you're a junior, now all of a sudden it becomes a little bit more applied and more direct to these specific topics. And the classes that we're talking about here, this class called Mechatronics, which is a hands-on lab class where you have to understand the basic electronic building blocks of test and measurement, and then apply those skills to measure engineering quantities, say pressure, temperature, et cetera, and then apply those to, say, automated systems, data analysis. You're going to take that class, and it's going to allow you to take those skills you learned these first 2 years and apply them directly to real engineering questions, real problems. The other professors and myself that teach that class, we actually draw a lot of experience from the professional world into that. So these are not just textbook made up things. These are real questions with real answers that you'll be able to actually do. And to the idea of selecting your major and kind of what you want to work on, once you're a junior, now you can kind of speak that language. You understand what's going on, and you can make these sort of informed decisions of, oh, I'm actually really interested in this or not interested in this. And by the time you're a senior, we give you the opportunity to explore exactly what you want. So the senior projects class at USC is relatively unique in that some schools work these projects like a competition, right? So everyone does the exact same project and whoever does the best gets an A. In our case, we say work on whatever you want. We give you a budget, we give you a lab, we give you a machine shop, we give you faculty support. And the idea is you could take your senior project at the end of your time at USC and say, here's what I'm interested in working on, and here's the proof. And so in an interview, if you said, oh, I'm really interested in working on the, what's a good example? I had a good example. A couple of years ago, I had a student design a CubeSat thruster. So they actually took a CubeSat and built a cold gas thruster with self-pressurizing propellant, valves, telemetry, everything. And they were able to go to a job interview and say, I'm really interested in working on small-scale spacecraft propulsion. Here's the proof. And they could present this item they've created in class that demonstrates what they want. And so the goal here is that over the course of those 3 years in the department, you're learning about engineering, you're learning about all these different fields, you're getting this hands-on experience. By the time you're a senior, you could start thinking about, hey, I'm really interested in this and I want to explore it. And USC gives you the option to do that. Another path for that exploration that's extracurricular to your classes is USC is particularly proud of our culture of design teams. And so in the AME department in particular, we have 6. And so with AME faculty, 7. We actually have
Assuming one involves a horse. Is that what you're saying?
Well,
And
8 if you include the horse.
If you consider USC Racing's or internal combustion engine team.
Yeah, this is two teams.
And then Formula
Combustion
SAE, so that's
electric.
our electric racing team. We also have Aero Design team. We have my team, which is Human Powered Vehicle or RVDT. We have USC Solar Car. We have Aspen, which is an organization that I run, giving students advanced spacecraft propulsion energy experience. And we also have our advanced composites design team under Professor Bo Jin. And so all of these teams, these are not restricted by major, they're just restricted to engineering students. And so let's say that you showed up and you say, oh, you know what, I'm actually really interested in electric vehicles. Great, you can join Formula SAE, get hands-on experience, be in that club from day one as a freshman. Say you wanted to explore aerodynamics, you can work with ADT. You want to explore human mechanical interaction, you can join my team. But this is for you to experience and gather these skills and take these opportunities to learn what you want, what you actually want to work on.
Thank you for that. Let's switch gears a little bit as we moved on from curriculum and talk about the other side of academia and research. Can we talk about what kind of research is going on in the department? Maybe Paul, we'll start with you, just kind of an overview of the types of areas, and then if anyone else wants to jump in with their specific research projects to give a little more depth and color to that.
Sure. Well, a lot of students ask the question of how do I get involved in research?
Mm-hmm.
And basically what I tell students is whether you're in somebody's class or even if you're not, you visit their website, you email them or come to their office hours and say, hey, I'm really interested in this. Is there some way I can get involved? What I do, and I think a lot of faculty do, is, if I think there's a good match, I will try to match up my undergraduate students with a PhD student, and then the PhD student will then be sort of the direct supervisor, and we'll try to find some little sliver of the PhD student's project that the undergraduate or master's student can then pick off and call their own. In terms of the type of research we do, we have a lot of faculty involved in aerodynamics, other aspects of fluid mechanics. We have one of the best wind tunnels actually in the world, low turbulence wind tunnels in the world. We have, in addition, in that what we call the Fabulous Fluids Facility, and Geoff is a core member of the Fabulous Fluids Facility faculty that we have, I think, really an outstanding fluid mechanics team. Myself and a couple of other faculty do research in combustion. We have people doing robotics. We have people doing design with including artificial. I'm sure this is a term that you've heard a lot recently, is artificial intelligence and machine learning. And we have some faculty involved in the design process, enhanced by AI, ML. And we have people doing biomechanics, that is looking at biological systems, but looking at them from the mechanical perspective. We find that traditional biologists are not necessarily very quantitative and not very analytical in the way that we are. I'm sure they think, they may have some opinions about us, but nevertheless, we have several faculty that are involved in the mechanics of biology.
Geoff, would you say that your research would be calculated as the Fabulous Fluids Facility for faculty for flight?
Quintuple F? Yeah, something like that. That's right. So it's true, I do research in this Fabulous Fluids Facility, and fabulous it is too. It's fabulous because fluids are fabulous in themselves, and they can produce both beautiful and complex and mystifying patterns that have practical consequence. And so the obvious aspect of that we're traditionally involved in is how aerodynamics work and how aerodynamics of wings and bodies work. And we're particularly interested these days in how aerodynamics work at smaller and smaller scales. So we're dealing less and less with 737 size things down to personal air taxi things, down to small drones that could fly about this room and surveil me and making sure I'm doing the work I'm supposed to be doing for my department chair. And so the question is, how do those aerodynamics work? And it turns out to be beautifully complicated and beautifully interesting. And we also work on a broad variety of fluid systems. Fluids are things that flow into the shape of any container that they're poured into. And so water is one of those. And so we do a lot of experiments with water, funnily enough, in an aerospace engineering department. And we do research on the tracks left by submerged vehicles for detection purposes. And we do a lot of research on mechanisms of drag reduction. So anytime a solid passes through a liquid or a fluid, then the friction resistance between the two causes drag, which costs money and reduces performance. So a large number of us are interested in one way or another about that. So I could talk for a long time about this, but I'll stop.
And then I can speak to a little bit to the research that I personally do. I work on diagnostics for advanced spacecraft propulsion development. And so in my research, we're looking at things that are used in space. So the thrust levels are 1/1,000,000th of a pound. And my little demo for that is if I took this Post-it note and I peeled off this much, and then I split that again, and I split that again, and I split that a fourth time and hold it in my hand, that's the amount of force that we're actually trying to measure. And so the question is how do you actually do that reliably, taking into account things like electrostatic attraction and electromagnetic interference? And we get down to some really fine point details, like the attraction of the two wires next to each other because there's current flowing in both wires, right? So it's almost like these problems out of your physics textbook in senior year high school physics, but come to life. It's a world where everything matters and you can't assume anything, which is pretty exciting. And so, project we worked on some projects where we were characterizing performance of electrospray thrusters. And right now I actually have students in the lab as we speak, building a fluid flow panel for a spacecraft on orbit refueling experiment through a grant through the Air Force Research Lab. So interesting spacecraft type work, but a little bit kind of like the person selling picks and shovels during the gold rush. We're not actually developing the spacecraft propulsion elements. We're creating the tools that allow us to learn about them and actually develop them. I also want to say that the students that are working in my lab right now, a plug for undergraduate research. In the past 2 years, USC has really grown their CURVE program, which is the Center for Undergraduate Research in Viterbi Engineering. And so the 3 students I have working for me right now are actually part of the CURVE program, which is an organization that you can apply to when you come into USC, and they help match undergraduates with research labs. And even better, they actually pay you a stipend for the first semester, the first year you're working in these labs. And so as someone who can provide research opportunities, CURVE's paying your stipend. And so it's great for me to be able to bring you in, say, as a freshman or a sophomore and give you some of that experience. So I actually have a true freshman that showed up in my lab on their first day at USC to start working on things. So CURVE's an amazing program. This year there were 400 applicants, and I believe they placed 200, 250 students into research labs across Viterbi. So this, research and these things that we can do for, hands-on experience at USC, undergraduates are absolutely included in this. And I'll use myself as an example. Like I said, I showed up at USC not knowing anything about anything and thinking I'm just going to work on airplanes. And I got a job as a freshman working in a spacecraft lab, and here we are, right?
Great, thank you. Can we talk about the next stages after undergraduate? And it doesn't necessarily need to be data driven. Anecdotal is fine, but where do these students go on to? I know we have students that go off into industry, the grand majority do, and some students go off to grad programs. Do we know what types of companies they're at and what they're doing, or what types of grad programs they're at?
Yeah, we do have data on that. And as one might expect, the largest number of our graduates go to work for Boeing. So both at the bachelor's and the master's level, the largest employer of our graduates is Boeing. Number 2 is Northrop Grumman. Number 3 for bachelor's students, I believe it's, at least in last year, it was Rivian, the electric truck manufacturer. Mm-hmm. For graduate students, it was I believe I have the acronym right, AMSI. It's a company that makes they don't make computer chips, they make the equipment to make computer chips. Because you see, even those, you say, well, isn't that electrical engineers? Well, no, there's a lot of mechanical systems, a lot of vacuum systems. There's a lot of, how do you make these, that is typically you fire electrons at some material and then it vaporizes and then it flows, well, it sort of scatters around and lands hopefully where you want it to on the substrate where you're trying to grow the chip. And so there's a lot of thermal issues with this, a lot of heat transfer and all that. So all of this requires mechanical engineers. I like to say that, heat transfer, even though it's kind of one of my areas of expertise, it's kind of a dry subject, but every engineered system has issues with heat transfer. And if you don't pay attention to it, that's what's going to come back to bite you. And so many times this happens. I hear from students say, well, I went there to work on, structures. And on the first day, the boss said, oh, we've, our biggest customer called and, our biggest selling product is overheating. Do you know anything about heat transfer? Can you help us out? And you wind up spending a career in heat transfer.
Any other companies you all want to throw out that students are going to?
SpaceX, of course, we send a lot of our graduates to SpaceX. I'm kind of surprised they didn't make the top 3 as of last year, but yeah.
Lots of students to other quote unquote new space or companies. So Blue Origin, we have a lot of students go to Relativity, which is founded by AME department alumni. So strong connections there. I'm gonna steal a line from Geoff Spedding in that Los Angeles really is the center of the universe. And so
it really is.
It really is. And so all of these companies, all this, especially on the aerospace side, this industry all exists here. And so USC is in a perfect position to make these connections and sort of tie into the, really ever expanding industry in the Southern California area across all these disciplines and all these companies. And so yeah, great student outcomes. I'll also have a small anecdote about this. To Paul's point about some of these upper division classes are kind of like spinach, right? You got to go through this process and learn these things. Every single summer, I get emails from students at SpaceX and Boeing and all these places, and the emails to the effect of, I can't believe this, but what you were teaching in class is exactly what I had to do in my internship. It was so hard in MECA, but I was able to do this exact thing in the internship. And my response is always, not shocked. But my response is always like, yes, like we actually, communicate with these, with what's needed in industry and our peers and our own experience to actually develop this curriculum so that we are teaching you things that are real and give you the skills needed to succeed and actually land these positions at a lot of these very competitive companies.
Fantastic.
I think the general point here also that underlies a lot of this is that the Southern California area is awash in small startup companies or even medium-sized startup companies. And so there's a range of options for graduates now, and at least for the next foreseeable 10 years or so, that is much, much broader and much more exciting than it used to be. So this is a good time to become an engineer. If anybody is wondering, mechanical and aerospace engineering is the place to be, and engineering in general is the thing to focus on.
This is going to be my last question that I'll ask in a moment, but I wanted to make sure that I told all of our guests that what I'm doing right now is opening up the Q&A for you to start asking questions. Here are the rules for the questions. No admission questions, nothing related to the application process, because we have faculty here from the department. This is specifically about the disciplines of aerospace mechanical engineering. So let's ask about that. If you want to attend any of our other events that we focus on admission, please do so. Lisa will put a link into the chat where you can register for one of our admission events where you talk in depth about admission and the application process and anything else related to this. We're not going to be answering those questions. So please put your questions in, and then keep throwing questions in, and then keep upvoting them. Because when you see those questions, we're going to make sure that you want to upvote them as much as you possibly can. And once those rise to the top, that's what we're going to answer right after I get to my last question here. So faculty, my last question before we get to the audience Q&A is the future. If you can get to your crystal balls or things that you know of, what are you excited about for the future of aerospace and mechanical engineering?
Well, I'll start with one thing. Couple of things that I can think of. Matt was talking about these very small thrusters. You might say, well, if that little thrust, why is it useful? I think one thing that's going to happen nowadays, we used to have, or we do have, these humongous satellites. I think what's the trend is to put up lots and lots of little satellites. And what we don't really have yet, and I think what Matt is doing, and what to some extent I'm trying to do, is to come up with more efficient propulsion systems for these small satellites. Think about, most of you have probably seen the movie Finding Nemo. And you know the scene where the fish rearrange themselves into different patterns? Well, imagine if we can do that in space with lots and lots of little satellites that you could do, then you have the flexibility to do things that one big satellite cannot do. But one of the limitations of that is these small satellites, the propulsion systems currently are not terribly efficient. And so that limits the lifetime of these small satellites. So that's one thing I'm very intrigued by. Another area of interest for me is getting more on the mechanical engineering side is, you think about your cell phone here, and what does it have? It has a battery in it. Now, how many, if you're coming here from the East Coast, are you going to fly here in a battery powered airplane? No. You're going to come here in a fuel powered airplane. Why? Because the energy density of hydrocarbon fuel is energy per kilogram is so much more than that of batteries. So the question is, why don't we put fuel inside of these phones? And that's one of the things that we're working on, is how to take the things we do everywhere in the world every day at large scales. We convert fuel into electricity. How do we do that effectively at small scales? And we have a number of things that we're working on in that regard.
Other thoughts?
Geoff, I think you know, well, either one.
I'm squirming away, waiting to say
Yes.
the future is fantastic and fabulous for all kinds of small-scale autonomous systems, whether they're interacting systems like Paul was alluding to there, or whether they're going on their own, whether they're exploring and bringing back intelligence. But the design space in general, with the advent of cheap computing, quite good batteries, GPS systems, and so on, it's now possible to make gadgets that we could only dream about before and test them out and see how they work. It's a fun time for exploring entirely new design spaces.
And with respects to our very robust combustion department in AME, we are very much in a generational, once in 100 years change in how energy is consumed and used, right? So a big example in your day-to-day life is, the electric car is now becoming, commonplace. And this type of shift in energy use is going to be evolving, over the course of my lifetime, and especially your lifetime. And it's something that I think is truly special, right? This is something that happens every, historically about 100 years, and we're there, right? It's all happening. And so this idea of how do we generate energy, how do we use it, how do we become more efficient, is going to create these amazing engineering opportunities and opportunities for us to really make a difference as mechanical, especially engineers that have to deal with these questions of efficiency and power and utilization. So
yeah, just no, go ahead, finish.
Personally, I find this time, if you step back and take 1,000-foot view of what's going on right now, you do have this, again, this, almost, beyond generational event that's happening. And the miniaturization and, ubiquity of computing power is giving these opportunities to be in Los Angeles, all these startups and small companies, et cetera. The world's really wide open.
Fantastic. Thank you very much. Now,
okay.
Before we dive
so
into...
I just wanted to say, just to follow up on Matt's thought, we went from horses, sorry, Cavalier, went from horses as our energy system to wood, to coal, to oil, and now we're going to electricity, battery storage. And it's about every 100 years or so that we make these shifts.
And another, when I'm 80 years old, my sports car is going to be in the stable for gasoline powered cars, right?
Yeah.
All right, so let's dive into our audience-driven Q&A. And as a reminder, you can keep adding questions in there. And I will remind you, as we're answering these, you should keep going in and upvoting, because new questions are being added and they might be getting lost down at the bottom. So please jump in and upvote those questions for all of you out there if you want to see those pop to the top. And the other thing I should have mentioned is that there was a lot of references to astronautical engineering in the conversation, because aerospace, mechanical, and astronautical engineering have a lot of overlapping curriculum, and students are interested usually in the overlapping areas of it, or want to know more about that. And we have a separate group of faculty from our astronautical engineering department holding this exact session later this week. So you can go to the link that Lisa put up, or maybe she could put it up again in case you missed it, on our events page to register for the astronautical engineering faculty session. So you've heard today why aerospace mechanical engineering is the best, and if you want to fight it out and see why astro, they might say they're better. We'll see. I don't know. They love the little rivalry between all of them. So please visit both of them and understand the differences. Well, but let's dive into the questions. First off, Paul has the Paul Melendres, not you, Professor Ronney, not me, but another Paul. We got 3 Pauls here. What would you recommend students do to prepare for AME the summer before starting college? I'll start this one just because I have a very personal perspective on this, and it does relate to admission, and I'll let you guys jump in. If we admit you, nothing. You've done the work through high school. The summer before you start college is your last summer before your life is controlled by everything else moving forward. So take that time to relax and enjoy your break from high school, because we got so much work waiting for you. And if you really want to do something, go get a job and earn some money that you can come to campus with. That's really my advice that I always tell students to do, but we've got plenty of curriculum waiting here for you. That's my thing, but I saw a lot of nodding, so I'll let you guys jump in if there's anything else.
That's the exact answer that I was going to say.
Okay.
Likewise, hit the beach or the mountains or a different country.
Yeah. Okay.
I will say, I found, and probably you, Geoff, have also seen this, is that if you're what determines to some extent, I mean, we try to keep our courses very self-contained. You don't have any prerequisites other than the ones that got you admitted. But I do find that some students had a very good high school physics background, and some had a weak high school physics background. And the one who had a weak high school physics background are going to be a little bit behind in my class, and probably in Geoff's class. So if you want to do, and I agree with everything that's been said, but if you want to do any studying or anything like that over the summer, I would review your physics, or if you just didn't have a good physics background. We've even had a couple of students that never, for some weird reason, actually never took high school physics. That's the thing that I would suggest reviewing, and I can even give you some pointers as to what books or what websites you could go to.
Great, thank you. Taylor asks our next popular question: how does the topic of sustainability play into the curriculum? Great question, Taylor.
Mm-hmm. Okay.
I think.
No. What I was going to say is
we can all talk
renewable
about
biofuel.
Exactly. No, one of the things I'd say is this. There's actually a lot of discussion right now about this idea of what does sustainability mean. And so in my previous answer, I said this is a really exciting time for engineering, because the problems du jour are efficiency, energy utilization, all of these things. This is what's being engineered. And so right now there's a little bit of debate over, well, do we put this stamp and say sustainability on what we're doing, when that's just what we've been doing anyway. And so in terms of that, sustainability from a marketing perspective, like, yes, we teach these, Paul's class, like energy and propulsion, talks about energy utilization, efficiencies, et cetera. We have our, human powered vehicle team focused on sustainability. We have Formula Electric, we have Solar Car, we have all these things within the department dealing with sustainability. But I would encourage this thought that is the challenge of our age right now. And in mechanical engineering, you're going to be learning the tools to develop these solutions. Not just because we say like, yes, well, we have these exactly as sustainability, but more because that's what the problems are. Like that's what we need to work on. And so you have to learn this as part of a mechanical engineering curriculum.
It's fascinating. We have so many students recently that are asking this question across everything. And we have so many students that are saying they want to study sustainability engineering or sustainable engineering. And because to be honest with you, I hate to say it's just a buzzword, right? They want to make a difference. Mm-hmm. And my answer always is sustainability is built into engineering across the board, mm-hmm. because these are parts of the problems that we're solving across the board. And there are some universities that are, I think, capitalizing on that buzz, and they're creating things related to sustainability when they just put a name on it, and it's built in. And I think that's what's most important to hear, is that's part of the core discipline.
Right, because even if you're, say, involved in, say, traditional combustion like I am, sustainability is utilizing the fuel that we're going to use to minimize the amount of fuel, to minimize the amount of carbon dioxide emissions. And also we're looking at, how biofuels burn differently than conventional fuels. I think about Geoff and some other faculty like Matul Luhar are working on drag reduction, which is another way of reducing our energy consumption, most of which still to this day in the transportation sector is built on burning something.
Can I skip a couple questions down to piggyback on this this idea? So if I hit answer live, that's not gonna hurt anything.
Just go ahead. Just go.
I'm doing it. Okay, so Liam, there's a student here that asked, opportunities for mechanical engineer and renewable energy, and this question of what can a mechanical engineer do for fusion energy? And I have a lot of peers and friends that work in the commercial fusion industry currently. And the short answer to that is everything, right? Everything but the plasma. And the idea here is if you're trying to do, any of these large companies like General Fusion, et cetera, the thing with fusion is what you're trying to do is keep the sun in a box. And Dr. Ronney just talked about the fact that, heat transfer always seems to be a problem, right? That's mechanical engineering. Right, the structures you need to keep a sun in a box, that's mechanical engineering. The intense magnetic fields and things you need for fusion that you actually have to have your system survive and not blow itself apart, that's mechanical engineering. And so this idea of, again, like this green energy and the ability to work in these fields, mechanical engineering is an extremely strong background to allow you to answer these questions.
This is
just to follow.
Please.
Just to follow up on that, a lot of people in my field are actually working on inertial confinement fusion, because the equations that describe as you try to use lasers to squeeze a little ball of deuterium and tritium to make, to make them fuse together, the equations that describe that are basically the same as we use for combustion. And so a number of us are working on that. And you have the same kind of instabilities, because if you don't do it just right, the thing will fizzle instead of start doing the fusion process. That's right within our wheelhouse.
This is another kind of context background to some of these questions, like to gather all of them together into a set, which is, I want to do something with this, whether it's a buzzword or some sort of end use purpose. And so people always say like, well, I like the idea of rockets. So does that mean I should be an astronautical engineer? Well, it's not just astronautical engineers making rockets. It's going to take aerospace engineers, mechanical engineers, computer scientists, electrical engineers, because these are complex systems. And then you're going to throw in systems engineers as well. And you're going to throw in material scientists. And you're going to throw in all these things. I mean, to Dr. Ronnie's point, nothing is one person doing one thing. It is a team of different areas. And when you're trying to decide to pull back on, I think, Geoff's answer before, it's going to involve all these elements, and you may be applied into that particular job down the road because that's what you want to do. But for your discipline right now, you're choosing a discipline that isn't an end use job. It's choosing a problem set or a context in which you're solving those problems that sounds interesting to you. Go after those things. You'll find your way to those elements of fusion engineering or rocket development or anything else we're talking about here. We're jumping between kind of abstract theoretical constructs to purposeful things that are being made to jobs. There's not directly a one line through those elements. So I appreciate all these questions. Armand asked a question. I'm curious to hear your response to this, Dr. Ronney. What are some limitations or downsides of mechanical engineering? He's like, so what's wrong with your program?
Oh,
that's what he's trying to find the problems, because he's got some critical thought going on here.
Oh, that's an interesting question. I guess the limitation is there isn't room in the curriculum for as many elective classes as we would like to be able to give you. That's the first thing that comes to mind.
Is there a limitation to the discipline?
To the discipline? That's an interesting thing. Well, I'll tell you, there is one thing I wish that our students knew more about, and that is chemistry. I know some of you say, ew, chemistry, but believe me, when you get right down to it, everything boils down to chemistry eventually, whether it's, conventional chemistry or in the case of fusion, nuclear chemistry, it all boils down to that. And a lot of it and that also materials. I'm fond of saying, even though it's not my field, we can do almost anything if we have the right material with the right structural properties, the right heat transfer, thermal conductivity, high or low, the right temperature resistance, the right catalytic properties if we're doing some kind of chemical reaction. So that's maybe the one limitation is I wish our, don't ignore chemistry.
Next question from Maggie. I'll kind of give a quick answer. You guys can decide whether you want to jump onto it or not. Is it common for students to complete internships and co-ops? Yes, absolutely. The idea that we talked about endpoint of jobs and all the companies that were listed, students are interning at those companies before. So it's very traditional to do that. We have our own career connections, our own career services staff in the Viterbi School to help you connect with these companies, internships, co-ops, full-time positions after graduation. It's very common. I've never known a student who have wanted an internship to not get one, because that's part of the process of moving you on to the next phase. We don't want to keep you. Our job is to get rid of you, to move you on to the next level, not just to bring you in. So like, we want to see you go too. That's an important part.
Very, very brief comment on that is our culture of design teams that give you these hands-on opportunities, starting from when you're a freshman, that makes it much easier to get those internships when you're a sophomore, junior, senior, because you're able to come to these interviews and recruiting events with hands-on experience already. And right. So that's something that we are very proud of here at USC.
Last minute warning for our audience. If you want anything to jump to the top of this list of questions, get back in there and upvote, because I think the upvoting stopped. So make sure that you get in there. Andrew asked a question on the topic of clubs and student organizations. How does a student get involved with Rocket Propulsion Lab, and what types of activities might a student work on there? Well, the easy answer is you go to the involvement fair that happens the second week of class for the engineering school. You go to their table and say, hey, I'd like to join. That's it.
That's it.
You just show up, man. That's really it. And students from all majors, that's another thing too about all the different clubs and the student design teams. Matt talked about all of these different things inside that are kind of related to aerospace mechanical engineering, but you don't have to be an aerospace mechanical engineer to get involved in these, nor are you limited to just those. Students get involved in lots of different organizations based on their interests. So just go sign up and talk to them. They always want more help.
Wait.
Please.
I've thought of a downside to mechanical engineering.
Yeah.
There are too many student clubs and organizations. There are too many possibilities. And so part and parcel of what we do. And actually, part of what I've been doing in lectures this semester is trying to encourage students to make sure they don't fill their plate too full of all of these opportunities.
That's a challenge. It's that finding that limit, finding that place where they are just doing enough, but not enough.
Yeah, I was going to say, I advise students that, take a look at everything and then try to focus on two things. One that's a curricular related activity, whether it's one of these design teams or research in a faculty member's lab, and something that has nothing to do with engineering, whether it's marching band or some other kind of music or some sort of sports or theater or whatever. But make sure you explore the full range of activities, not just technical ones when you're here, because you'll never have this opportunity again.
Great. And then I'm going to ask one more from our list of Q&A. And then if you all want to take over, if you find one down the list that you want to grab at, so you can grab your own. But the last one I'm going to ask is from Maxwell. Asks, how easy is it to switch majors within Viterbi? If you're admitted to the Viterbi School of Engineering and you want to change your major, you can always change your major to any other major in the Viterbi School of Engineering. We're not taking any raised hands, Telly. Sorry, we're just going through the Q&A. So it's a democratic process. So anyways, if you've been admitted to the Viterbi School of Engineering and you want to change, you can change. And more often than not, the things we've talked about with aerospace, mechanical, and astronautical engineering, which is usually where students are struggling with this pre-application, students enter in one of these and always graduate in another one. That's pretty common. These are fairly common, and there's no timeline on when you need to do that. That's a very fluid process, pun intended. There's lots of stuff that people kind of move between these. So don't worry at all about it. We want you to be successful in the engineering school. Do you all have any favorite questions here you want to ask? I'll let you take over. Matt, do you see anything there that you want to grab?
The one that's at the top of the list for elaborating on Formula SAE, in terms of how to get involved, you just show up to the involvement fair and say, I would like to join. How that club is run, it's an incredible team that is competing every year. It's about 40, 50 students, run by Professor Jan Stalens. And if you actually go to USC's racing websites, if you just Google USC racing, you can actually view some amazing videos, descriptions of sub teams. Absolutely an incredible experience. That team is also very strongly supported by our Baum Family Makerspace, which is a facility at USC purely dedicated for undergraduate hands-on learning and experience. And so this was completely built. It's got CNC machines, water jet, laser cutters, 3D printers. If you can think of it, you can build it. And what's even more interesting is it's not just limited to design teams. As an undergrad at USC, you can walk into the makerspace and say, I want to make something. And they will help you do it, right? If you want to work on a custom part for your motorcycle, they can help you make it yourself and use CNC machines to build it, et cetera. It doesn't have to be related to class. So I thought that was interesting to plug USC Racing, but also plug the that, again, more hands-on experience that you have here at USC.
Geoff, you see anything you want to address, or anything you'd like to just say that we haven't covered?
I would like to talk about engineering in general.
Yeah.
And Matt said something that caught my interest. He said, in this project, everything matters and you can't assume anything. By contrast, I quite like engineering because you have to assume some things, because you have to solve problems, practical problems. And so I take great pleasure in making the most ridiculous possible assumptions just to make my life easier, to see whether the problem works or not, to see whether the solutions can be used. And so part of engineering, I think, is a playful exploration of alternative worlds that you create in your mind and on paper, and then see which ones you can put into practice. I think it's a very important part of engineering, this sort of exploration through the space of equations and systems that we learn about.
Thank you. Dr. Ronney, you get the final word.
Yeah. Oh, okay. I noticed there's
Any other questions?
a number of questions are about design. And how does design fit into our curriculum? Well, even in the freshman class, you take computer-aided design, whether you're in 101 or 105, for mechanical engineers, aerospace engineers. And in 105, you build a glider. In my class, you do two design projects. One is to build robot cars that try to push each other off the top of a ramp, a hill. We call it King of the Hill. And the second project is to design and build a bridge. And it's 3D printed, but you have to, first draw it out in CAD. You have to virtually test it, with the stress analysis software that you learn to use during the class. And then once you have a design that looks good, and this is a team project, there were a lot of questions also about team projects. You design it as a team. You can come up with your own designs and see whose works the best. And then once you have something that looks good, at least according to the computations, then we 3D print it and then we test it. And then in the end, then you see, well, of course, the performance does not always agree with what you predicted according to the computational analysis. And then the challenge is to know, how do I decide why it didn't work according to the computations? I'm fond of saying that's where the science ends and the art begins. And we want to teach you not just the science of engineering, but also the art of engineering. And I think all these hands-on experiences, either within the classroom or these other extracurricular activities, really helps you build up your expertise in the art of engineering.
This is great. And I think there's no better note to end on than that. Thank you all for joining us for today's session. Lots of great questions and lots of great information regarding this one. As a reminder, we have other events that are happening with other faculty, with recordings of events that have already gone on and future events that are happening, all on our events page that are in the chat. And where you register for this one, you can register for another one. But most importantly, thank you to our faculty for taking time out of their day to speak with each of you. So Professor Gilpin, Professor Spedding, Professor Ronney, truly appreciate your time. Thank you all, everybody. We'll end the recording now.
And thank Cavalier.
Oh, I'm sorry. And thank you, Vice Chair Cavalier.
Yeah.
I never feel good about talking to a horse. I don't know why. Thank you all.
I'm used to it.
We'll see you all later. Thank you, folks.
Okay.